Another day, another story. When Stephen Hawking died on the 14th of March, the famed theoretical physicist had a few papers still in the works. Today, the Journal of High Energy Physics published his last work in cosmology, the science of how the universe sprang into being and evolved. In this video, we'll explore Hawking's and Thomas Hertog's groundbreaking research and attempt to unravel the mysteries of the universe's birth and evolution. Cosmic inflation is a monumental growth spurt that supposedly stretched the infant universe during the first tiniest fraction of a second. Dreamed up in 1979 by American theorist Alan Guth, inflation holds that just after the Big Bang, space stretched exponentially, doubling the size of the universe again and again at least 60 times over before slowing dramatically. But why would cosmologists believe in something so bizarre? Inflation solves a major puzzle. Why is the universe so uniform? For example, space is filled with radiation lingering from the Big Bang, the cosmic microwave background, CMB. It has almost exactly the same temperature everywhere in the sky. Inflation solves that puzzle by implying that all the points in the sky started out close enough to interact, and then were stretched far apart. Ironically, inflation also does a great job of explaining why the universe isn't completely uniform. Space is studded with galaxies, and inflation stretched infinitesimal quantum fluctuations in those first moments to extragalactic size. The fluctuations then produced variations in the dense soup of fundamental particles that seeded the formation of the galaxies. Inflation predicts a particular spectrum of longer and shorter fluctuations, and studies of the CMB and the galaxies confirm that distribution. But here's where the concept of inflation runs into problems. Physicists dislike the idea that inflation would stop suddenly, for no particular reason. They'd much rather have a mechanism that explains what drove inflation and then caused it to stop. That's why they assume some sort of quantum field drove it, before petering out. The problem is, the exponentially expanding false vacuum produces more and more of itself, potentially leading to an ever-increasing number of universes, each with its own unique characteristics. This notion of a multiverse could challenge cosmologists' attempts to explain fundamental constants and the nature of our universe. Hawking and Hertog propose a bold solution in their paper. They argue that eternal inflation does not occur. To support this claim, they borrow a concept from string theory, equating two different types of theories with different dimensionalities. They suggest that under certain conditions in the early universe, a maneuver like this can be used to view the situation in a space with one less dimension, leading to a single, well-behaved universe instead of eternal inflation. This concept is known as holography, where one theory can be equated to another in a space with fewer dimensions. In Hawking's and Hertog's theory, the very early universe should be described by a theory with just 3 spatial dimensions and no time, challenging our conventional understanding of spacetime. This bold approach also tackles one of the most persistent problems in cosmology: the singularity at the moment of the Big Bang. By eliminating time from the equation, theorists aim to avoid this troublesome singularity that has long puzzled scientists. While Hawking's and Hertog's work presents a promising avenue for addressing the mysteries of the universe's birth and evolution, there's much more to explore and understand. The concept of eternal inflation and the Big Bang singularity remain topics of ongoing research and debate in the scientific community. As we delve deeper into the cosmos, we continue to uncover new layers of complexity that challenge our understanding of the universe. Thanks for watching.